In this chapter, we're working with scale representations. In this lesson, we're looking at scale drawings and models. We'll start with reviewing proportional reasoning.
All right, hi everybody. So in this chapter we're going to look at scale drawings and models. Okay, this will be the first lesson in this chapter here. But before we get into that, what we're going to do is we're going to do a really quick review of proportional reasoning. Okay, now you would have taken a look at proportional reasoning actually in probably several earlier math courses, whether they specifically addressed it as proportional reasoning or not. That's what you would have done. In Math 10-3, you would have talked about it explicitly. We would have talked about it as proportional reasoning. But you see this in basically every math course you would take. At some point here, there's probably going to be some proportional reasoning in it. So let's just talk about some of the things that pop up here. So a ratio is a comparison of number with the same units. Okay, with the same units. Now, practically speaking, we don't often, I shouldn't say we don't often. We will often set up ratios that aren't quite technically the same units there. Like you'll see stuff on maps where you'll see like an inch to a kilometer or something weird like that. But for the most part, when we're talking about ratios, that's what we mean. We've got the same units here. And because they're the same units here, we don't have to write the units because the units are irrelevant at that point. If the units are relevant, then you have to plug them in. If you're using different units there, then they have to be in there, those units. A rate is a comparison of numbers with different units, and the units are stated. Okay, so that might be a better way to write it if the units are different there. But kilometers per hour, like oftentimes when you see rate, okay, rate is frequently per unit of time. It doesn't have to be, okay, because you can have variables changing with respect to other variables changing. A proportion is a statement of equal ratios or rates. Okay, so when we set them two together here, so often you'll see it as two fractions set equal to each other. So like A over B is equal to C over D. Okay, and that's when you set it up like that, that's something you can solve because you can what we call cross multiply here. We know that A times D is going to be equal to B times C. Okay, and just like it says here, to solve a proportion, you're going to cross multiply, and then typically you would have to divide. So a great example of that, for example, are the percentage calculations. If you want to figure out what 22% of 15 is, well, we know that when we write it like this as a percentage, that symbol there means it's out of 100. So in this case here, we would be looking at 22 out of 100. And we're trying to find what 22% is out of 15. So like it says here, is what we don't know here, out of 15. So we're going to put 15 in the denominator. And you would cross multiply and then divide. So it would be x times 100. So you might even start off like this. 100x is equal to 22 times 15. Okay, and then we would divide by 100. We get 3.3. Anyway, now let's take a look at some examples. All right, now let's jump into some questions here. So we're going to solve for the missing variable out of these proportions that we've got here. And we're going to do it just like we said, we're going to do it by cross multiplication. So 4 times 100 is going to equal 25 times x. And then I'm going to divide by 25 here. So it'll end up being 400 over 25 is equal to x. And after we do that, and you can pull out your calculator there if you'd like. Okay, but 400 over 25 is not that hard. 400 divided by 25 is going to equal 16. Whoops. Sorry. Caught my finger there. There we go, 16. That's all it is. So, 13 times 4. Okay, we're going to do that over here. Let's just figure that out. 13 times 4, just want to make sure I get that. 52 is going to equal x times 52, or 52x here. Now, when you divide both sides, you're going to divide them by 52. Because to get the x by itself, remember, you're always going to divide by the coefficient of the variable, the x. And when you divide 52 by 52, I mean, the beautiful thing is you just get 1. There we go. That's what x is. Here we're going to cross multiply, so 1 times 256 is going to equal 8 times x. And then again, I'm going to divide by the coefficient of the x there. So I'm going to divide both sides by 8. And when I do that, I get 32. Now over here, we're going to start to work with proportions here that are used to convert units of rate or whatever. You're going to see this sort of thing used well in different contexts. So, but you've got two different units going on here. So, but again, we cross multiply, so it's like 450. Now this is interesting because we multiply the units together. So we got kilometers times hours, which is a little weird, and then we're going to get x kilometers times 5 hours. Now, bear in mind, I'm going to keep the unit together here with the variable here, and then that 5 hours. So now what I'm going to do is I'm going to divide by 5 hours. So we're going to get 450 kilometer hours, and we're going to divide by 5 hours. So what's going to happen here is when you divide by the 5 hours, we're going to count that 5 out. 450 divided by 5 will be 90. But then the units are going to cancel. The h's will cancel, and what we're left with will be the kilometers. So our x kilometers here is going to be 90 kilometers. So you can see how the units survive, and it's the correct unit. As long as you've done it properly here, the correct unit is going to survive here. Let's do this again here. So 10 meters times x seconds. So maybe we go 10 meters, okay, x seconds. Now we're going to multiply that through, and then 15 times 5 is going to be 75. This is going to be meters seconds. And I want to get seconds by itself. I want to get x seconds, so I'm going to divide by 10 meters here. And so when I divide, whoops, sorry, I probably want to keep that unit there. Keep that unit. X seconds is going to equal, well, I'm going to divide 75 by 10 to get 7.5, and then the meters are going to cancel, and the unit that I'm left with there is seconds, so 7.5 seconds. Okay. Now, we do something similar here, and I had kind of hinted at this before when we do some sort of conversion. I want to make this 15 kilometers per hour. I want to set that equal to x meters per second. Okay? So what I got to do here is I've got 15 kilometers per 1 hour. And at some point here, I want this to be x meters per 1 second. Well, I need to have, in order to make this conversion here, I need these units to be the same, at least numerator to denominator here. So this is what we're going to do. Sorry, I didn't give myself enough room. But what I'm going to do here is I'm going to convert kilometers into meters here. So to convert kilometers to meters, I want the kilometer in the denominator because I want the units to cancel. And I know that there's going to be 1,000 meters in 1 kilometer. Now that's fantastic. Kilometers will cancel. I'll multiply that out here. I'll be left with meters in the numerator, which is what I want because on the other side it's going to be meters. But I don't want hours in the denominator. I want seconds. Well, I know that 1 hour, just like I've given you here, 3,600 seconds, okay, is going to be x meters per 1 second. Now, when I do the conversion here, it'll be really quite straightforward. Sorry, when I do the solving for the x there, it'll be really quite easy at the end because of that 1 second here. But let's multiply this out here. This becomes the hours are going to cancel, the kilometers are going to cancel. I'm going to be left with 15,000 meters over, and then again the hours canceled here. I'm going to be left with, and just multiply that up here, 3,600 seconds is equal to x over 1 second. Now, when we cross multiply, we're going to get 50. Actually, I'm going to end up running into this in here. I'm sorry. I'm going to get 15,000 meter seconds is going to equal, and x is meters, x meters 3,600 seconds. And when I divide, I will divide out to cancel the seconds, and you get 15,000 divided by 3,600. I'm just doing that on my calculator, and I'm going to get approximately let's say to the nearest tenth here, 4.2 meters per second. Whoops. Sorry, that's not what I want. Sorry, I just wanted to know what x was. So it's going to be meters. However, I know that when I bring that back up to here, that means it's going to end up being 4.2 meters per second. So that's 15 kilometers per hour will be the same as 4.2 meters per second. Now, 15% of a number is 12. Okay, find the number of a number is 12. So with 15%, that's 15 over 100. Sorry, I got to move over a little bit. I just didn't give myself enough room. And is 12. Well, remember the little hint that we had up here. The is number goes up in the numerator, and the of number goes in the denominator. So I don't know what it is out of, so my x is going to go down there. So now I'm going to cross multiply, so it'll be 1200 is equal to 15x. And then I'm going to divide 1200 by that 15. You divide it by the coefficient of the x here, and we get 80. So we know that 12 is 15% of 80. Okay, so I hope that helps. Of all these ones here, this was probably the most, and I guess the most confusing because I had the most work here. But really what it was just a matter of converting, okay, doing that conversion first before doing the cross multiplication. And it wasn't important that they were all in exactly the same units, but we needed to make sure that like the numerators had the same units and the denominators had the same units in order for us to make sense of what was going on there. All right, now let's talk about scale factors. So proportional figures have the same shape, but a different size. Okay, so like it says here, you can think of it as like model airplanes, model cars, whatever. Or think of it like this: if you've got like a picture on your cell phone and you just kind of zoom in, sort of thing, you get a bigger picture, but it's the same picture, right? Same shapes that you're looking at, just the different sizes here, but they're proportional to each other. So just like it says right here, the figures can be enlarged or reduced, right? You can zoom in or zoom out here. But you've always got the starting figure, and we're going to call that the object. Okay. So that's where we start. That's the object that we're starting with, the information that we're starting with, and then we're going to do something to it. So we can enlarge or reduce, okay, which in math we call that a transformation. Okay, it's a transform of it, by multiplying the object's dimensions by a scale factor. Okay, so the figure that's produced is the finishing figure. Oftentimes we're going to call it the image. So you've got some starting point, your object, you're going to do something to it, either make it larger or make it smaller, then that becomes the image of the original object. And so here we go. There are three formulas that model this relationship. So image dimensions, where you take the object dimensions and multiply by the scale factors. Okay. Object dimensions, where you take the image dimensions and we divide by the scale factor. So it depends on which direction you're going. If you know the object and you want the original, okay, or sorry, not the original. If you know the object, if you know the original, and you want the image's dimensions, then you just multiply by the scale factor. If you've got the image's dimensions and you want the object's dimensions, the original, you divide by that scale factor. And then to get the scale factor is simply going to be the image dimensions divided by the object dimensions. Now, in order for this to make sense, you really got to be clear on what we mean by image and object. Until the distinction between those is really clear, then this doesn't really make much sense. So you got to be careful and just read that through and make sure you've given just a little bit of time to it. If the scale factor is larger than 1, then your image is larger than the original. That's an enlargement. If the scale factor is smaller than 1, then it's a reduction. You're looking at something that's smaller. Okay? And so here we go. Just a little note here. Students can get asked questions that will involve solving for the image dimensions, the object dimensions, or the scale factor. So you need to be versatile. You need to be able to address any one of those questions there. Okay, so this question asks us to calculate the scale factor here. So we're just going to go through some examples here. So remember that the scale factor is going to be the image, okay, the image dimensions over the object dimensions. Now we're going to do this. We're going to do this a couple of different times here. So I'm basically going to write this out once. Then we'll just do it for each one of these things here. So here's the original. Here's the new. Okay. So it's an equilateral triangle. I can tell because of the way they've marked the shapes, the sides here. So is this one. And I'm going from 8 centimeters to this 6 centimeter one. So the original starts at 8. The new one, the image, is at 6 here. But that means that image dimension is 6 centimeters over 8 centimeters. Notice that I've got centimeters over centimeters, so those are going to cancel. And 6 over 8, that can be reduced. There's a factor of 2 in each of those. So if I divide 6 by 2, I get 3. 8 by 2, and I get 4. So the linear dimensions here, no, not the area. area is a little different. Just the length of the sides here. These ones here are 3/4 of the original. So because this is smaller than 1, it has been a reduction. I mean, I can see that from the diagram, but just to be clear, the math follows that. Here, same thing. We've got our scale factor. It's going to be, okay, image. Okay, I might even just like this. Let's say image dimensions over object dimensions. Give myself a little bit more room here. So here's the original. Here's the new. Now, to make sure that this is scaled up, okay, what I need to see here is I need to see that each dimension is being multiplied by the same amount here. So I'm not even going to worry so much about like the scale factor right now. I just want to make sure that there's a common multiple here, and then I'll figure out how that scale factor looks in a second. To go from 30 inches to 90 inches, I multiplied by 3. 18 to 54, I multiplied by 3. 16 to 48, I multiplied by 3. Okay, that's important, because what that means is it's the same thing with every dimension. So this has just been scaled up. Let's use 90 here, then it doesn't matter which one. And I know that the image goes in the numerator. So it'll be 90 inches over 30 inches. The inches will cancel. And yeah, just like I was working with here, it's 3. The scale factor is 3. The image is 3 times larger. Okay. Now, that could have gone the other way. It could have been 1/3, whatever. I wasn't sure. All I know is I just wanted to make sure that it was the common multiple between each of these before I even tried to figure out what the scale factor is. I just wanted to make sure it was consistent. And it is. And the answer is 3. Let's take a look at another one here. All right. Connor McDavid is 1.85 meters tall. What scale factor was used if his hockey card has a picture of him measuring 13.2 centimeters? Okay, so remember our scale factor is going to be image dimension over object dimension. Now, in this case here we've got 13.2 centimeters, and here we've got 1.85 meters. Now, the thing is, I can't come up with a scale factor right now because my units aren't the same. They're not going to cancel. In a scale factor, the units really should cancel. Okay? So to be a proper scale factor, like I was saying before, sometimes we don't. Sometimes in like maps and whatnot, we leave the dimensions in and we assume that people are making that kind of conversion correctly in their head. However, it's a lot more straightforward if I just make sure that everything's in the same units here. So if I have 13.2 centimeters, I'm going to leave this as centimeters. Let's convert the meters into centimeters. I'm going to move the decimal 2 over. So it'll be 185 centimeters. That's way nicer here. Okay, I'm going to go to the calculator here. I'm going to pull this out. 13.2 divided by 185. This is work out. That's kind of a crazy number here. So this is approximately 0.07 as my scale factor, which is clearly substantially smaller than 1. So this is a substantial reduction. However, I'm really just curious. I'm going to press the math button. Because of the calculator that I have here, I'm going to press my math button right now. Just take a look at something. The very first option I have is convert to fractions. I'm going to choose that. Okay, so I get 66 over 925 as my scale factor. Well, I'll be honest with you, that doesn't communicate a whole lot to me. In fact, in this particular case here, the decimal communicates a lot more to me. Because when I look at this, I could even easily convert this into a percentage, and it becomes 7%. And I know that my image is therefore 7% the size of the original. Just offers me a couple of different ways of interpreting that. Okay, in this question, we're looking for the image dimensions. So the distance between Edmonton and Calgary is 299.6 kilometers. What is the distance between Edmonton and Calgary on a map if the scale is 10 centimeters to 100 kilometers? Okay, so here's an example of what I was hinting at before, where, okay, we've got a scale here where the units are different. Now, on another page here, we said that a scale factor, the dimensions should be the same. And yeah, that's technically true, but practically speaking, that's just not what happens here. So, but as long as we're consistent with our units, we're okay. So what we've got here, and I'll write it this way. Okay, we've got 10 centimeters over 100 kilometers. I think it's easier to work with it in fraction form here. I know that this is image over actual. What I'm interested in, what is the distance between Edmonton and Calgary on the map? So I'm looking for X centimeters on the map, but I know that this is 299.6 kilometers, okay, in actuality. So now I'm going to cross multiply, and I'm going to get, when I multiply these together, it's going to be 2,996 centimeters times kilometers. It's going to equal X centimeters times 100 kilometers. And then I'm going to divide by that 100 kilometers. It's going to cancel with the kilometers, and when you divide that by 100, you'll get 29.96 centimeters is equal to X centimeters. So there it is right there. Edmonton and Calgary would be 29.96 kilometers apart on the map. Okay, let's take a look at this one. Sam builds a model car that has a scale factor of 1 to 10. Okay, so the units aren't mentioned here. It's because the units are not important. This works with any units here. If the original car's length is 2.5 meters, how long is the model car? Okay, so let's go for it again here. So this is 1 to 10. So we're looking at a reduction here. So this is the image, this is the original. So what is the original car's length? So if the original car's length is 2.5 meters, so down here we've got 2.5 meters. We're looking for the model, and this is going to be in meters. We're going to cross multiply, so we'll get 2.5. And notice that the units stay. There were no units over here, so this is great. I love that. I love this. And then this will be 10 times x, or x times 10 meters. Okay. Now I can divide by 10. Now I could divide by meters on both sides and cancel those, but I know that my answer is going to be in meters here, so I'll just leave it out here. Sorry. Did that the wrong way. I have to divide by 10, not multiply by 10. Is going to be x meters. So 0.25 meters is x meters. That's how long the model is. And then over here, a picture has dimensions 4 by 6 inches. What are the dimensions? The picture's new dimensions if it is enlarged by a factor of 3. Okay, 4 by 6 here. Now, if we enlarge this by a factor of 3, what we're doing is exactly what this says, by a factor of. Now, that means multiply by, okay, multiply by 3. So 4 multiplied by 3, 12. So 12 inches. 6 multiplied by 3, 18 inches. Okay. You would have seen on the other page here that when we talk about, I'll just make sure I'll show you again. When we talk about image dimensions, okay, we take the object dimensions and just multiply by the scale factor. Well, that's exactly what we're doing. Here, if we're going to do this by 250%, in order to really make sense of that, I have to understand that that percent sign means 250 over 100. Now I'm going to multiply by that scale factor, but I'm probably going to simplify that a little bit first here. I'm going to divide 250 by 100, make that 2.50. This is what I'm going to multiply by. So 4 times 2.50 is going to be 10. Okay, so this would be 10 inches. 6 multiplied by 2.50 is going to be 15 inches. And so, those are the dimensions of the new picture after those two enlargements there. So now, in this small set of questions here, we're going to be looking for the object dimensions. So a model train is 25 centimeters long. What is the real train's length if the model was built with a 1 to 125 scale? And again, that's a proper scale here. So it'll be object length over real. And I know that my model train is going to be 25 centimeters. And so my real train's length is going to be down here, x centimeters. And notice it's going to be in centimeters. Now it's going to be big, but it's going to be in centimeters here. So we're going to multiply across here. 1 times x centimeters will be x centimeters. Absolutely love that. Love the fact that that turned out like that. So it's just 1 times x. And then it's going to be 125 times 25. And I get 3,125 centimeters. Okay, well that doesn't communicate a lot to me. And so what I might do with this is convert these things to meters. And it's very easy to convert that 3,125 centimeters to meters. That is the same as, just divide by 100, 31.25 meters. And actually, in my mind, this communicates way more to me because I have a better idea of what a meter is and what 31 meters would look like. I do know what a centimeter is, but this idea of 3,000 centimeters or 3,100 centimeters, that's less clear to me than writing it in this form. Okay, let's look at another one. So a world map has a scale of 5 centimeters to 100 kilometers. So again, not a truly a true scale here, but image over reality. What is the actual distance between Vancouver and Winnipeg if on the map it's 114.7 centimeters? That's a big map. Okay, and then this is going to be X kilometers. I don't know what that is. So we're going to cross multiply. We're going to get 5 centimeters by X kilometers. And I'm going to just multiply these two together. That is going to be, I'm going to move that 2 over, 11470 centimeters times kilometers. Okay, so 11,470 centimeters times kilometers here. Well, that doesn't make much sense until I divide by that 5 centimeters. And so X kilometers is going to equal, okay, the centimeters are going to cancel, and I'm going to get 11470 divided by that 5. Okay, so what is that? 2,294. 2,294, and the units that survived there were kilometers. Okay, that's a long way away. Catherine works in design, and she has a poster that was made from a picture. What were the dimensions of the picture if the poster measures 1.5 meters by 1 meter? Okay, so here we go. 1.5 meters by 1.0 meters. And it was enlarged by 250% to reach that size. Okay, it was enlarged to get to this size. Okay, now remember the original dimensions, if you think back just a couple pages ago here, are going to be image dimensions divided by the scale factor. So in this case here, our original, let's say our original length is going to be 1.5 meters divided by our scale factor. Now, okay, we got to take a moment here and remember that scale factor. And we used that scale factor just a few moments ago. We convert 250% into that ratio, 250 over 100. That's percentage over 100. And I'm just going to divide that, make that 2.5. Okay, and so then I go to my calculator here and I get 1.5 divided by 2.5. And I get 0.6. So 0.6 meters. Sorry. I don't know what went up there. That didn't make any sense. Now if I go and do the original width, that's going to be 1.0 meters divided by my scale factor, 2.5. Okay? And so 1.0 divided by 2.5, and I get 0.4 meters. Okay, so that's how we would go backwards to the original length here. So notice that at some points here we're cross-multiplying and dividing. At sometimes I'm just going to divide by that scale factor. And most of the time when I do that, it's when I have a nice, just a number, not a ratio, but like a number as my scale factor. It just works really well. And it doesn't matter how you do it as long as you're consistent with the way the information is given to you. All right, now we're just going to work through some questions that are mixed questions. So they're not divided into different categories, so we have to be able to look at it and figure out what we're supposed to do. So the ratio of the length to width of a rectangle is 10 to 7. Okay, good. Nice true scale, no units given. How long is the rectangle if it is 5 meters wide? Okay, so the ratio of the length to the width, so we've got length, and we even put it up here, length to width, okay, is going to be 10 to 7, is going to be how long is the rectangle. So I don't know what the length is, but I know that the width is 5 meters. This is just a matter of cross multiply and divide. So 10 times 5 will be 50 meters. 7 times x, and x is going to be in meters. It'll be because this there's no units here. Whatever unit I'm given, that's going to be the unit we're going to work with. So essentially just going to take 50 now and divide by 7, just to move it to the other side. And it doesn't work out to be a nice number. It's like 7.1 meters approximately is equal to x. But that's what you would get here. Let's have a look at another one here. A 4-foot tall bird standing next to a globe casts a 14-foot shadow. If the globe casts a shadow that is 7 feet long, then how tall is it? Okay. Well, the nice thing is we're working, it's just feet here. It's all feet. So a 4-foot tall bird, there's the original, casts a 14-foot shadow. That's the image of the bird here. So 14 feet, 4 feet. And in this case here, my units don't even matter, but I'm just going to leave them in here anyway. But they don't matter because they're all the same. If the globe casts a shadow that is 7 feet long, now that's the image, so 7 feet long, how tall is it? So this is what we're looking for here. We're looking for the units of the original. Okay? So if we cross multiply here, x times 14, you're going to get 14x, and this is going to be feet by feet. Okay? Yeah, we could write that here, but really, I know that my answer is going to end up being in feet. All the feet are going to cancel. It's going to end up being feet. This is going to be 28 feet times feet, like feet squared, and then I'm going to divide. And when you divide 14 into both sides here, 28 divided by 14 is going to be 2. And so that's how tall the globe is. It's going to be 2 feet. Okay? Because remember, this is like, if you want me to put it in here, 14 feet, x feet. This is 28 feet. This is so weird. And we cancel that, and we're left with 2 feet. Okay? Just to be consistent with some of the notation we've seen previous to this. A map has a scale of 1 inch to 16 miles. Okay? So not a true scale, but it's totally something we can work with. If Victoria and Johnston are 9 inches apart on the map, then how far apart are the real cities? So 1 inch, 16 miles. We're looking for how far apart they are in reality. So that's going to be x down here. This is where the image is. So this is going to be in miles. I want to make sure I get that. Up here, this will be 9 inches. So we'll cross multiply here. 1 inch mile, x mile here. And that is going to be, well, okay, 9 times 16. And I knew that. 144. This is going to be inches times miles. And then I'm going to divide by that 1 inch. I'm going to get the x miles here is 144 miles. So that's how far apart these cities actually are. And again, I'm just using the scale. Okay, I'm rewriting it as a fraction, but that's all we're doing. And then over here we've got a model plane is 3 inches tall. Okay, so that's the model. If it is built with a scale of 1 inch to 6 feet, again, not a true scale, then how tall is the real plane here? So we know the scale is model to actual, and in this case we know the model is 3 inches. What we don't know is the actual. We'll cross multiply, and we're seeing something very similar that to what we just did here. So this will be 1 inch times x feet here, and when I multiply those, I'm going to get 18, but I've got inches times feet. But I'm going to divide by that inch to get how many feet were there? Well, there were 18 feet. So this thing was 18 feet tall. And so there you go. Just some examples of how to do proportional reasoning and working with scale factors and whatnot.